Let's talk now about alpha addition to asymmetric ketones. Now what we're going to see here is that depending upon the conditions that we're using, we could possibly end up with a product where the uh, alkyl group ended up on the more substituted side or on the less substituted side of the asymmetric ketone. And all of this is going to hinge upon thermodynamics and kinetics. So this is going to be a similar discussion to what we had when we talked about that competition reaction with the dienes. Let me give you an example of that. So over here you can see we've got two examples. We've got this one here which has the triethylamine in the heat, and this is going to end up substituting on the more substituted side of the asymmetric ketone. And here we're using LDA at minus 78 degrees, and the alkyl group ends up on the less substituted side of the asymmetric ketone. So what we're looking at here is a competition in itself. We'll talk first about the kinetic conditions, and if you'll remember what we talked about with the dienes, we said that kinetics was all about the comparison of activation energies. So you can see that the activation energy to form the anion from this one from B is very much lower than the activation energy required to get the proton off this one here. So we're looking at the comparison between how easy it is to get this proton and how easy it is to get this one. Now what I would say is that this proton here is far more exposed than this proton is. So this one is much easier to remove. That means it needs a lower activation energy. So this one would be favored to be removed at lower temperature if we had a strong base. So we're going to use kinetic conditions to form this product, which I'm calling B. And of course, once we got the anion, that's what would react with the alkyl halide to form the substituted asymmetric ketone. Now this one ends up substituting on the least substituted side because that's where the negative charge ends up. But if we were to raise the temperature and use thermodynamic conditions, we end up getting a more stable anion, and we'll remember that thermodynamics is all about the stability of the products, while kinetics is about the activation energies. So the stability of the products here, the negative charge being on the more substituted carbon, is actually favored because it has a resonance structure that leaves a very substituted double bond on this side, whereas this negative charge, which is on the least substituted side, has a less substituted double bond when it resonates. So this anion ends up being more stable. Since this anion is more stable, it is going to be preferred to be formed if the temperature is higher. So this is going to be an irreversible type process, and it's possible that we might get both anions formed because the activation energy allows it, but the one that we'll end up with at the end, if we let this sit for a bit, is we'll end up with this particular anion which has the negative charge on the more substituted carbon of the asymmetric ketone. Then this negative can go ahead and react and give us the product that we see here, where the alkyl group is attached to the more substituted carbon of the asymmetric ketone. Alright, let's take a look at the mechanism for this, and I'll do the kinetic one first. Alright, thermodynamic up here for this one. By the way, it's always a dead giveaway for thermodynamic and kinetic. Is it the conditions that it's under? Thermodynamic is always done with lots of heat, because the activation energy doesn't matter when there's lots of heat, because both activation energies are going to be doable with heat. Kinetic is always at low temperature, and that ensures that we get the product that results from just the one with the lower activation energy. Alright, back to what we were doing. So what we're going to do is we're going to have the LDA come in, and the LDA, as we learned earlier, looks like this. lithium diisopropyl amide. Negative comes in, takes the proton, and it's going to take the proton off the less substituted side because the activation energy is lower to do that, and we're at low temperature, so we know we're looking at kinetic conditions here. And then we can have the negative charge come in and attack the alkyl halide, and that's how we're going to end up with our product. And as you can see, the alkyl group ends up on the least substituted side under kinetic conditions. Looking at the thermodynamic conditions, even though this proton is harder to abstract, under the kinetic conditions, under these thermodynamic conditions, what's going to happen is the nitrogen will take the proton off the more substituted carbon, because it's going to be a more stable anion. And then we can have the negative attack the Br, the negative to see with the Br. And kick out the Br. And that's how we're going to end up with the other product here. It's going to have the alkyl group on the more substituted carbon atom.